This is an integral that shows up a lot in electrostatics, like if you're finding like the electric field due to like a linearly charged rod a distance d away. This shows up a bunch, and yeah, I mean, I think most colleges will just give you like a table of integrals and this will be on it, or like on an AP Physics C test, they'll tell you like it is given that the solution to this integral is whatever, right? But I thought I could still show you guys how to solve it, because it's actually not too bad. So it's integral of dx over, x squared plus a squared to the 3/2 power, which just looks pretty nasty, but it's not terrible if you know how to approach it. Well, how do you approach it? If you've taken calculus, hopefully you can kind of see that, you could maybe try like a trig substitution. So if you don't know what trig substitution is, basically, mathematicians kind of realize that, wait, hey, when you have like an x squared plus a squared kind of situation, right? That's like kind of like the hypotenuse of a triangle. So if I were to kind of draw this out, if you pretended this was a triangle, you could say, well, this is x squared, x, right? And then a, and by sorry, I usually move my chair out of the way here. Sorry about that. You can use Pythagorean theorem to be like, okay, well, the hypotenuse would be square root a squared plus x squared, right? And this is the x squared plus a squared part. So I can kind of rewrite this in terms of trig. Because if I think about this angle right here, I'll call it phi. I know that tan of phi is then equal x over a. So I can rewrite what I have here in terms of this stuff to make the integral a little bit easier. So let's do that. So integral dx over x squared plus a squared 3/2 is equal to this stuff. So, well, not equal to this stuff. I don't know why I said that. I meant we're going to jump back here and kind of rewrite this stuff, because I know that x, if I multiply both sides by a, I get x is equal to a tan phi. And then what is dx going to be equal to, right? If I took dx, so if I did, dx over d phi, it would be equal to a secant squared phi. So I know dx is going to equal a secant squared phi d phi. So I can now start to substitute things in back in my integral. I could say integral, this integral is really just dx over, so x is this, so I could say a tan phi squared plus a squared, right? A squared, and then, at 3/2 power, and there's this dx, so what I can do is I can just really change this out to this stuff, a secant squared phi d phi. Okay, so I've rerun my integral. Now I just got to simplify it to make it solvable. So if I were to rewrite this again, integral, so a secant squared phi d phi over, now you're gonna want to square the a tan phi, so it's gonna be a squared tan squared phi plus a squared to the 3/2, and hopefully you can kind of notice that, hey, wait, in the denominator I have a squared on both terms. If I were to factor those out, a squared tan squared phi plus 1 3/2, and then this is a secant squared phi d phi. If I were, to take that out, tan squared phi plus 1, that's a trig identity. That's secant squared phi. So I can even rewrite this part to be secant squared phi. So now I get integral of a secant squared phi d phi over a squared secant squared phi to the 3/2. So now we can start, now this is like a product of two things. I can kind of distribute the 3/2. A squared to the 3/2 power, the 2, right? You're doing your exponent properties. 2 times 3/2 is just 3. Same thing for secant squared. So I can really rewrite this as a secant squared phi, integral, a secant squared phi d phi over a cubed secant cubed phi. Okay, so a over a cubed, that's just 1 over a squared. I can actually just pull that out of my integral, so let's do it. Let's do it here. We do it here, and then we'll use this once we are desperately running out of space. So 1 over a squared integral. So secant squared over secant cubed would be just 1 over secant, right? So d phi over secant phi. But remember, secant phi is just the inverse of cosine phi. So if I have this in the denominator, it's really the same thing as 1 over a squared integral cosine phi d phi. All right, so 1 over a squared integral cosine phi d phi, that's pretty simple. That's just, so if I do it now here, equal to 1 over a squared times sine phi plus c, right? So that the 1 over a squared times sine phi plus c, I don't want phi in my answer, and you could be like, oh well, I can take the inverse phi, or the inverse tangent of x over a, plug that in. But the easier way to just kind of do it is, this is my angle phi. I know sine phi is just going to be opposite over hypotenuse. So I could say it's equal to 1 over a squared times my opposite is x over square root x squared plus a squared plus c. And that's really just the answer. So I could say, this is usually how they'll write it. A squared plus c. So yeah, there you go. Hopefully that was helpful, and you got something out of this. Thank you for watching.